Good afternoon, class. My name is Ali Marar, and I'll be presenting my final term project. I chose the topic of smart city cluster computing, and then what we'll do is we'll do a synopsis of smart cities, cluster computing, and we'll focus on a power system load forecasting model that I developed, which implements cluster computing. So first of all, what is the concept of a smart city? Smart cities lead to a sustainable future of the city. Um, Populations are growing, people are moving to the urban environments within a city. So cities are facing aging infrastructure, aging populations, many government mandates about implicating about greenhouse gases and carbon effects. With cities have shrinking budgets, um, energy and water resources are becoming more and more sparse and critical. Therefore, we need to develop a model that would bring economic prosperity, resource conservation, and social well-being to a city. So this is a picture here of a smart city that I found online. Um, Basically, smart city implementation can be brought in as small as a traffic automatic traffic automation, or all the way up to taking care of traffic management, education, social well-being, air pollution, and so on. So it can the model needs to be scalable, and the smart city concept is scalable in of itself. So when we look at it, we're looking to optimize the smart city concept in general. Now we're going to be focusing on a power system load forecasting model that implements smart city on the power system side, but that's just a um, small part of the equation here that we're looking at. So the power of cloud computing. Cloud computing, um, the objective of cloud computing, let's say, it's supposed to bring in faster implementation time because the computing is done on multiple servers or computers on a large scale. It should lower the total cost of ownership, especially that the fact that there are no physical resources that a owner must is implicated with. So there's none of that server, or the cost is basically shared. We're looking for enhanced security and scalability, which is big. You know, as the system grows, the computing needs to grow as well. The smart city concept essentially is considered part of the IoT, Internet of Things. It's a data and statistical model that is strictly data driven and driven by the sensing and field devices. Now, essentially, the human or the population is considered a field device that is driving the some of the inputs of the model, as well as um, devices that could simply be cell phones, could be traffic cameras, um, or just servers that are bringing in data into the model. So these are just all things that can be considered as sensing and field devices, which are driving the model. Um, Concept of smart city requires state-of-the-art computing. The fog computing concept is very much researched right now when it comes to smart cities. Um, because the communication infrastructure needs to be strong, number one, but because there's no central computer driving this, it really relies on the multiple computers and the multiple servers and the multiple devices that are deployed in the field. So by using fog computing, the the algorithm could be clustered across many different areas, and then the the outputs come back in and are exhibited or forecasted. Smart grid to smart cities, like I said, it's a multi-application and it's a big unified network. So what we're focusing on in this project is power system load forecasting, but the smart city concept could be anywhere from, like I said, resource management, water, sewer, trash, electric, people's well-being, medical, and the whole objective here is to yield the most economic and highest performing option. Smart city load forecasting. So smart city as a concept is basically just a large forecasting model. Um, in this project, we're going to predict the electrical power required to meet the short-term, medium-term, and long-term demand. To keep in consideration, really, everyone forecasts to be, or all industries forecast to be productive. So, for example, airlines are constantly forecasting what their demand is on flights. They're trying to see if their flights are completely booked or not. Manufacturing is looking at their demand so they can meet their demand with manufacturing, since it's got to be a long-term plan. Financial markets are projecting prices of the financial market, all based on forecast. So smart city in of itself is just a large forecasting model, and then the power system load forecasting model we're going to focus in this project is just another forecasting model. So all in all, if we implement our power system load forecasting model in a way that's scalable, we can implement this same model on any other forecasting model. So we can take our power system load forecasting model and implement it on water or sewer or trash, or we may be able to tweak it up and implement it into the financial market. So our problem statement for this particular project is there's a lack of an accurate dynamic load forecasting model, which in this particular case impacts frequency stabilization, economic dispatch, CO2 or greenhouse, and so it's an environmental issue, power system stability, and then the optimized deployment of generating resources, specifically renewable. And then our objective here is to utilize previous load data. Since we don't have access to the field devices, we're using load data that is recorded by the New York Independent System Operator from their database, which is available online. And we're also using weather data from the National Climatic Data Center. And we're going to use that data to determine future load forecasts and then compare to what the load forecast was. Right here, this is just some snapshots of the data that is available from the NYISO and some of the screenshots from their website as well. And like I said, this data is just historical data that they make available for research purposes. Same here, this is from the National Climatic Data Center. It's just strictly from their website, just screenshots. Data modeling. So this is the beginning of the algorithm or the forecasting model. So data modeling there's many forms of it. In this particular case, we're going to focus on regression and neural network models. I'm just bringing regression because that's just the classical old school method that everyone seems to lean towards. Regressions are just predictive model techniques that investigate relationships between independent and dependent variables. So if the independent variable X dictates that, this is how hot it is, then Y says this is how much power we need to produce. Now this is an old school model, it's dummy, there's no, although it is a data-driven model, there's no decision making or there's no artificial techniques that are constantly optimizing the model. The other form of data modeling, which all of our focus will be on, is artificial neural networks. And for the last 10 years, this has been a very growing and developing field because of the optimization of computing and processing systems. So artificial neural networks provide the capability to support nonlinear mapping of input and output variables. When compared to regression models, there are some nonlinear regression models, but they do not bring the dynamic capability of what artificial neural networks bring. They provide a lot of robust performance in noisy environments. They're able to take the outliers and completely trash them and focus on the data that actually counts. And they are models that, as they train more and more, they get better at what they need to do. So the data doesn't always have to be administered because the neural network is taking care of that in of itself. And then they make decisions based on level of confidence, and that's part of the AI that the data model, the artificial neural network. For the sake of this project, we need to evaluate some performance evaluations or metrics. And the reason we need to do that is because we need to make a valid comparison, a like for like or apples for apples comparison between our data and our results. So when our results are clustered versus we implement feature selection and extraction, we need to be able to see where our improvement is being done and if there is any. So in this case, we're using the mean absolute percentage error, which basically measures the prediction accuracy of the model. And we're also using the RMSE, the root mean square error metric, which measures the standard deviation of the residuals of the model. So basically, it's basically telling us how far away are we from being correct or incorrect. We'll use MATLAB for the evaluation, and in this case, there is a regression widget that MATLAB brings. Now we'll also hard code some of the some of this model has been hard coded, but in this case, we're going to focus on the MATLAB evaluation to begin with. And the nice thing about the regression widget is that it provides different types of regressions, including artificial neural networks and support vector machine models that we can utilize to compare to see what would be the best option moving. So here's some of the results of our regression. As you can see, the root mean square error and the MAP are plotted here and or tabulated, and we get our best results from the supervised machine learning, which is a AI artificial neural network algorithm. So it's a significant reduction in the metric, which yields a positive result. So the supervised machine learning algorithm uses SVM support vector machine learning, which basically, when compared to a regression, provides a snake-like approach to the regression. It bends itself around the data to create a best fit model. Now, the way it does that is it encodes its data and compiles it in its own type of compiler and then retranslates it into a way that this vector machine learning algorithm can provide the most optimized results. After we ran our base artificial neural network model, we implemented feature selection to the model. Feature selection basically brings the advantage of reducing the amount of irrelevant data. It filters out redundant data, removes dimensionality from the data, and then maximizes the learning accuracy. It's basically here, what we're doing is we're looking at what similar features bring the most optimization to the model. Similar when you're buying a car. When you're buying a car, a feature could be paint color, and a feature can also be, the amount of horsepower in the engine, or if the interior is leather or not. So basically, we're looking at the features that make the most sense to sell the car, or in the perspective of the purchaser of the vehicle. Why do we use feature selection? We can improve our training speed significantly and the predictive power because we're basically making the model more simple to the computer or to the processing component of the computer. Also, like I said, we're removing dimensionality and removing the noise. So this brings, it's like I said, we're simplifying what counts to make this performance, to maximize the performance of the algorithm. And So to sum it all up, and I'm pretty sure I went over on time, but it's hard to do everything when there's such a limited amount of time. But to sum it all up, smart city implementation is just a large forecasting model. In this case, we were able to forecast and efficiently evaluate the metrics of a power system load forecasting model. But the true reality is smart city is a large forecasting model. So by implementing fog computing, by implementing clustering, by implementing feature selection, we're able to optimize these large forecasting models. Now, when comparing to big data analytics, computing power, we need to look into these innovative computing approaches because these models tend to have millions and at times maybe even billions of fields that need to be computed if we want to look at a large smart city approach. So we need to make sure that whatever algorithm and whatever model set up needs to be scalable. Um, Power system load forecasting model that we implemented, like I said, is just a small branch of the smart city concept, but it is one of the most vital branches, in my opinion, of smart city concept as someone that works in the power system industry. And it is also, I would say, one of the forecasting um, that can be implemented in other sectors of the smart city, whether it comes to communication, water, sewer, electricity. Like I said, it's the concept is the same. We're just taking the concept and tweaking it a little bit to fit that particular type of application. And we were able to apply neural network, supervised and unsupervised machine learning, feature selection and extraction, and clustering to optimize a forecast model. Um, I really enjoyed this class and this project, although it was something that I worked on for almost a month and a half, if not two. It was a bit challenging, and hopefully, if everything goes good, this would be my last project as a graduate student, as I hope to graduate in the next few days. So I appreciate all the efforts and everything that was done by everyone. Thank you.